There are a couple variants of the rotating disc electrode that people have used. One of the more popular ones is the hydrodynamically modulated rotating disc electrode. The idea here is that we can use an electrode that's rotating and, as a function of time, modulate the rotation rate. So in other words, the normal average rotation velocity or rotation rate in radians per second would be some average value, let's call that W0. But in actual fact, what you would do is modulate the rotation velocity so that you would end up with that average value of the modulation of the rotation rate. So you would have at the end a modulated velocity rotation rate, which we'll call it 2 delta omega. And usually that modulation amplitude is fairly small. So we'll modulate it by, say, 1 to 10 hertz while we're rotating, say, at 10,000 hertz. And so what you would get out is the normal signal, but you can use a filter to isolate. First of all, you can isolate the average rotation signal, the I that you would get out, and that would look just like a signal here. But then you can also use a filter that isolates the frequency-dependent part of the signal, and we'll call that delta I. And delta I would just be equal to delta omega over omega 0 to the 1/2 times the I omega 0 term, which is just the current, the average current that you would get without the modulation. So you just see some fractional amount here. So this is omega with time, and then the current with time would be similar. The idea here is that this sort of method is now completely insensitive to things like adsorption or double air charging and other background processes. For example, suppose we had a signal that had some adsorption process involved with it. And remember with the CV, if we had adsorption, we get a little peak, a pre-peak or a following peak. Same thing would happen with the RDE, and we'd get a peak like this, or something similar, depending on the strength of the absorption. Or you might see a peak here or somewhere else. So this would be very difficult to analyze with the normal voltammetry. But since we're looking at the modulated signal now, these peaks do not end up being part of the signal that's modulated, because this modulation signal is only part of the signal that's affected by convective mass transport, and the absorption is not affected by absorption by mass transport by convection. It's only and there's not affected by diffusion either. So you isolate that, and you can remove some of those effects. So it can be useful, particularly for signals, for example, that are overlapping or affected by strong background absorption processes, and so on. Now, we've only talked about the rotating disc electrode in detail, but there are some other geometries that we mentioned. The tubular geometry, with a radius, internal radius, and a length, like so. And you can derive the limiting current. It's equal to 1.61 times 10 to the minus 6 NF C0 star dA over R to the 2/3 times V to the 1/3, where the V is the volume flow rate. I believe cubic centimeters per second, something like that. So we're flowing that material through. And as you can see, the faster we flow the volume, make the flow, the higher the current is going to be. Can you think of a problem with this sort of an electrode that you don't really have so much with the rotating disc electrode? One of the reasons this sort of electrode is not so popular, especially in this tube-shaped geometry, notice there's no L term in here. Why would there not be any effect of L on the geometry? Well, one of the reasons is that most of the tube is wasted. You don't need, all the reactions are going to occur as soon as you get inside the tube, essentially. And so you really don't need the L term there. It doesn't really matter how long it is. And so it's what they call a non-uniformly accessible electrode. The current will be variable along the electrode itself. So the amount of current that flows at any particular spot on that tube varies. And that's a problem because if we're doing kinetic studies, remember when we took a look at kinetics, we're really looking at the amount of reaction occurring on the electrode, and that is reflected by the amount of current that's flowing on the electrode at any particular spot. So if more current's flowing on some part of the electrode than the other part of the electrode, that means that the rate constant at some part of the electrode is effectively different than some other part of the electrode. And so that, of course, is a very difficult problem to solve, and it makes it very difficult to understand the kinetic effects. So this sort of geometry, okay for analytical purposes, but not generally useful for kinetic measurements. Rotating disc electrodes is what they call a uniformly accessible electrode. Means that there's a current density is fairly uniform across the electrode surface, and you can analyze the kinetic effects fairly simply that way. Another type of electrode that has got a uniformly accessible electrode is a channel electrode. The idea here is that you make a very well-defined channel and you embed it close to the end of the channel, an electrode that extends across the channel. So this would have a side view like this and a top view like so. And you can pump solution actually quite rapidly through that channel, so the mass transport rate is very fast, but still maintain a uniform accessibility. Because of the channel dimensions, it maintains a laminar flow, and you get good mass transport rates. You get good kinetic results with this sort of electrode because it's uniformly accessible. I'm going to leave off more discussions of hydrodynamic electrodes. We've got the paper to talk about today, which talks a little bit about that. But I'm going to talk. You can look a lot of times. There's a book chapter called Hydrodynamic Voltammetry and Continuous Flow Analysis. Now this is really for analytical chemistry, but it does mention the types of hydrodynamic voltammetry that people are using, particularly for analytical purposes. Written by a guy named Gunnissingham and Fleet. And it's a book chapter in the series by Bard called Electroanalytical Chemistry, Volume 16. 1989. So it's not too far out of date. Channel electrodes came came about a little bit after that. A lot of the theory developed a little bit later than that, so there's not a lot of channel electrodes in here. And so we'll leave it at that. We can talk a long, long time about hydrodynamic voltammetry, but I think we've covered a lot of the introductory stuff, enough for you to get some more information on your own. Okay, what's the time? I think since we've got a little bit more time, what we'll do is we'll start the next chapter